So I'm going to talk about robust computational MRI with deep learning. And before that, I just want to talk about what computational MRI means. So in my definition, computational MRI is the idea of jointly using computation to jointly design how we acquire measurements from the MRI system and how we recover it or reconstruct it into an image. And to do this, we use knowledge of the system plus heavy computation to redesign how data is acquired. We use prior knowledge, right? We know that we're scanning a particular subject, and so we want to use that information. But we also want to use the prior knowledge of all of the previous patients and subjects that we've scanned before when we design. And what sets us apart from other computer vision-like tasks is that we also want to take advantage of the imaging physics. So we want to design our system in a way, and our algorithms in a way that obey the physical laws of our imaging system. And kind of taking a step back, we can even think about this idea of not only jointly designing the acquisition and the reconstruction, but also how we do the analysis and the reporting, right? We can connect all of this diagnostic imaging pipeline together. But my focus is really on the first two parts. We kind of try to hand off good quality images to the radiologist without necessarily interfering with how they do their job at the moment. And so before I dive into the details, I want to mention a little bit of background about MRI. So in MRI, we're collecting data in the Fourier space or K-space. And so the signal, the image that we get from the MRI machine is not the raw image, but it's the measurements in this domain called the frequency domain. Let's see if I have a pointer. And it's our job to basically collect all of these red dots. And once we have enough red dots, we can do our image reconstruction. But it's important to remember that also this data are complex valued. And so this is another differentiating factor from conventional computer vision or image processing methods that have been developed. And this is kind of what the process looks like. So on the left, we're collecting K-space data. And as we collect it, we reconstruct an image on the right. And as we collect more and more measurements, we get a higher and higher quality image. And each of these measurements just takes a certain amount of time to collect. And so this kind of dictates our scan time based on our resolution and SNR requirements. And so our scan time is proportional to the number of data points that we collect. And so if we collect enough data, we get a high quality image. But if we collect less data, for instance, this is a 2 times faster scan, then based on the MRI physics, we know that we'll get this kind of artifact, which is called coherent aliasing. But it's up to us to design how we acquire the data, so we can also change the acquisition in different ways. Here, we're still collecting less data, so we have artifacts in our image. It's not quite as sharp as before, but these artifacts look a little bit more benign, and we want to take advantage of this idea when we design our reconstruction methods. And so the name of the game is this idea of collecting data and then figuring out how to recover the image from these limited measurements. And we call this the inverse problem. We're going from the forward process to the inverse to get the image. And the problem is that we just don't have enough measurements to do this in a really routine way. We're going to need to use computational machinery in order to accomplish that. And we call this in our domain ill-posed. And what was done in the past is that these methods were regularized with handcrafted models. So borrowing from the mathematics domain, people designed these handcrafted models that are really good for image compression. And they use them in a way to regularize the solution so that we're not looking for any old image, but we're looking for an image that, for instance, has a small number of non-zero coefficients in what's called the wavelet domain, which is used in JPEG. Or, for example, if we're looking at this cardiac video, an MRI heartbeat over time, then the temporal difference is very sparse, so there's a very small rate of change or innovation in this data. But these were all handcrafted, right? So these were hand-designed by mathematicians and engineers for a different task. But ultimately, it all kind of gets buried into this term, which we would call the prior, and it's how we're incorporating information about our images into the reconstruction. And this idea, which is called compressed sensing, is actually used in the clinic. So every major MRI vendor has implemented this idea. And you can go get an MRI scan today and potentially be using this kind of technology that speeds up the acquisition by factors of up to 2 to 3 relative to what was done before. So it's actually having a significant effect. And the turnaround time for this was about 10 years, just for kind of frame of reference. So what's the problem? Well, compressed sensing is really good, but but it's a little bit naive in the sense that we're using this information, this redundancy in images that wasn't really designed in the first place for medical images. And so this idea of a sparse prior is not necessarily the most informative for what we care about. And in addition, the reconstruction algorithm is not necessarily the best choice. And so this is where deep learning has come into play in the last few years, where we replace this, this iterative reconstruction algorithm with kind of this, what we'll call a black box, right? So some deep learning algorithm that goes from the raw measurements to the image reconstruction. And there's kind of two generic ways that we can categorize deep learning inversion. One is end-to-end supervised training, which I'm sure many of you are familiar with. And then the other, which I'll highlight, is distribution learning or generative modeling. Okay, so in end-to-end supervised learning, what do? We take our bucket of raw data, the Ys, this is our case-based data, and we take a bucket of our ground truth images. These are clean images that we'll use for training. And then we design our reconstruction algorithm, potentially using deep learning, say a convolutional neural network. And we get some image at the start before we train, but we compare that to our ground truth image, and we use that to update the weights of the network. And as we update the weights of the network, we get a better and better quality image. And these things are actually unbelievable in their performance. So what I'm showing here is a challenge that Facebook and NYU ran a couple years ago called the Fast MRI Challenge. And as I scroll through, all of these methods are deep learning-based methods. This is a leaderboard. And as we get all the way towards the bottom, keep going, eventually we hit the baseline compressed sensing method. That was the method that I showed at the start. And so these deep learning methods are just blowing away the classical methods out of the water. It's really quite remarkable at how much they are able to accelerate the acquisition compared to what we were doing before with handcrafted models. So what's the problem? The issue is that end-to-end supervised training, even though it is really great, it's really great when the conditions at training time are matched to the conditions at test time. And when you're in a hospital environment, that's really hard to control. Right? We don't know if we're going to have the same exact patient population with the same exact MRI scan parameters, with the same exact SNR levels, and all of these variations can cause changes in the performance of the method. And so in particular, these deep networks are designed explicitly to be coupled to the measurement process, which means that I have to choose how I'm going to undersample the data before I train my neural network, before I train the deep learning reconstruction. And so if I train it with a sampling pattern that looks like this is the data that I collect in the Fourier domain, I get a good image. But if the sampling pattern changes, which is a common thing that we do in MRI, this is called changing the readout direction, then we actually get a degradation in image quality. And so this means that we would need to retrain for all of these different scenarios, or come up with a scheme that can handle all of these different types of scenarios. A second example of this is when there's motion in the data. And so this is showing a ground truth image, an image without motion. And this is the image after motion has happened during the scan. But we can train a deep network to remove this motion. All good. But the problem is that if the acquisition pattern changes, then these methods will degrade as well. And so we would again need to tune our method or train it a priori without knowing what kind of motion to expect. And that's just not possible to really deploy this in a clinical way. A second issue is that these methods are really tuned to the specific anatomy. So for example, if I know that I'm going to scan knee images, then I should train a deep network for knee image reconstruction. And if I have brain images, I should train one for brain. But if we apply one to the other, for example, this is showing training on brain and then testing or applying on knee. What we would really like to see is the performance to follow this dotted diagonal line, but we have this drop in performance. And the way to overcome this drop is to essentially fine-tune, take new data and update the weights of your network. But to do that, you would need a lot of data because these networks are very large. A third drawback of end-to-end supervised training is that there's no really built-in way to know how are we sure that we got a good result. So this idea of uncertainty estimation. We can design end-to-end networks that can give us this kind of risk map, this uncertainty estimate. But we have to design it ahead of time with this in mind. And potentially we could come up with ways of retrofitting supervised networks to do it, but it's not really built into the process. And so what we do is we go back to the basics. Let's start with what our MRI signal model is. We know that we're measuring in the Fourier domain. We have some noise. And let's think of this from a probabilistic point of view. The conventional reconstruction methods are essentially doing some form of penalized maximum likelihood, which means that we want to find the highest probability of data that matches a certain image. But what we want to do is we want to model what images look like, and in particular what medical images look like, or specifically MR images, or even more specifically brain MR images, or maybe even just T2-weighted brain MR images, right? We want to use all the information we have. And so this idea of prior knowledge, which originally we used with compressed sensing of modeling sparsity and compression, we really want to just learn what the distribution of images looks like. If we have that information, then we could compute the posterior distribution and basically say, let's find the image that's most likely given the measurements that we've acquired. And so the trick is, how do we get this prior distribution? And that's where this idea of generative modeling comes into play. And so what we will do is, instead of using deep learning to do an end-to-end reconstruction, we will use deep learning to model this prior distribution. If we can come up with a way of sampling from this distribution, then we could, for example, sample images of brains. And so none of these brains are real brains. They're all sampled from this prior distribution. But they have a lot of similarity in structure with real T2 brain-weighted images. And this idea is that we want to decouple, explicitly decouple the prior from the measurement model. We want to just use the deep learning machinery to learn the prior. We don't want to model the measurement process because we already know the measurement process quite well. We have a good notion of the physics of the system. And then we'll use this Bayesian approach to sample from the posterior. So why generative models? Well, generative modeling is really powerful. These are some examples of using a generative model trained on a particular class of images and then generating new images, right? So none of these images are of real people. They're all sampled from this prior. There's a nice website you can go to, thiscatdoesnotexist.com. Every time you hit refresh, it'll show you another picture of a cat that doesn't exist. And I was playing with Dolly earlier this month, and I gave it this prompt: a young white professor with a man bun performs medical imaging research. All right, and it made a nice new profile photo for my website, right? So these things are really powerful. And we want to leverage this power, but we want to tailor it to the medical imaging domain. So let's tailor it to the medical imaging domain. What's the problem? Well, when people design those generative models, they usually benchmark them on what I will call this benchmark inverse problem. It starts with a picture of a celebrity. Often it's Obama. Hope you all voted today. And these images are RGB, so they're positive everywhere, or non-negative, with a max value of 255. And we use this simplified matrix called a random Gaussian matrix. It's very different than the way MRI works. And then we get our data. But MRI is very different. First of all, we have an image that's complex valued. Secondly, we actually measure it with multiple receive coils, so we get multiple channels of the data. Third, we do a continuous time Fourier transform, so we're going from a continuous object to a continuous Fourier space, and then we get measurements in the Fourier space, and they're not random measurements. And in addition, there's also a temporal component, because we're collecting data in a certain order, so they don't all come at the same time. And all of these differences make a huge effect on when we use these generative models. In addition, the stakes are higher, right? So this is from my colleagues. They have a nice paper on using these methods, and they reconstruct Obama from a limited number of measurements, and they describe the result as giving superior visual reconstructions. And here's a state-of-the-art method applied to brain. Again, this is from the Fast MRI Challenge. And even though the reconstructed brain image looks really nice, you might notice in this by this red arrow, this artifact that was produced generated a false vessel, possibly related to susceptibility artifacts right here, introduced by surgical staples, right? So the stakes are higher. We can't just say, hey, the image looks good. We actually want to know, what confidence do we have that this is the correct reconstruction? And then the way that we approach this is using something called score models. And so what we did is we trained a score model, a generative model, on brain images. And then we designed a reconstruction algorithm that takes advantage of the prior and uses the measurement model at the same time. And it's competitive with end-to-end methods, meaning that it matches supervised learning when the test conditions and training conditions match. But importantly, it works really well when the conditions differ, and that's because we're not modeling the so-called conditions when we train. We keep that explicitly separate. And really, the machinery behind this is something called score-based generative models. It's kind of the state of the art at generating fake images from a distribution. And without going into too much detail, the idea of these score models is that if we give it an image as an input, it will tell us in what direction to update our estimate that is a higher likelihood image. So if we start here with these low probability images, these are all images with artifacts. If we pass it through our score model, it will tell us, hey, move to a new location in your space that is a more likely image. And so this is showing using score models for generating new images. So it starts with pure noise. And every time we run it through our model, it tells us, hey, update the image to look a little bit more like what I know to be true images. And this was trained on images from a particular computer vision data set. And so by running the algorithm, starting with pure noise, I can generate new images from my distribution. So how do we use that with MRI? In MRI, we don't want to just generate any arbitrary image. We want to generate the image that matches our data. We want to find the image X that best matches the data Y. We want to actually sample from this distribution. So we'll call that posterior sampling. But we run the algorithm in a very similar way. We will start with a very low likelihood image, just pure noise. And the score model will tell us in what direction to update. How do we update the pixels of this image, not only to match our prior knowledge of what images look like, but also to match our measurements. And in this way, we will get an image that is both consistent with the measurements and matches our prior knowledge of what MR images look like. We can also run this multiple times. I can start with a different random noise instance and run the algorithm again, and I'll get another sample from the posterior. So I can run this algorithm multiple times and get different samples, right? Because there's uncertainty. We don't know, we don't have all the measurements, so we can't know for certain that what we're recovering is the so-called true image. There's many images that match the data. OK, I'm going to skip this, but I just wanted to mention that we also have robustness guarantees. So we can say, if you run this kind of method, what is the, how far away are you from the so-called best possible solution? And these kind of methods are very powerful because of these types of guarantees. What we did is we ran this on the same challenge data set that I showed before. Question? Oh, a few more minutes? Yeah. OK, thanks. All right, I'll skip some of the details of the training setup, but I just want to mention some results. Here we're emulating a 10 times faster scan. This is the classical method. This is end-to-end supervised learning. And then this is what we're able to achieve at this high acceleration because explicitly we're decoupling the measurement model from the prior. We can also apply this to different anatomies. So here I'm doing this on knee images, and this is just a zoom in of the part that most clinicians care about. I'll skip the data there. But we can also run it. Here's an example of running it on an image where we have actual pathology, this faint line. And you can see in our reconstruction the faint line as well. But we can take that and we can run multiple instances of our algorithm and then create an uncertainty map. So we can say, how bad is our reconstruction? Am I certain or am I uncertain about a certain region? And this is the true error, and it matches our uncertainty map. And so kind of summarizing that idea, I can sample from my posterior. I can run multiple samples and get an average. I can take that average, those multiple samples and get an uncertainty map. And the uncertainty map very closely matches the true error, in this case where I know what the true image is. We also ran this at Dell Medical School at UT Austin on some subjects. So in a completely different hospital, completely different MRI scanner, completely different patient population. And we're able to do this prospectively. So this was a 4 times faster scan. We didn't even collect the data, so we don't know what the ground truth looks like. The final thing I'll mention, I'll skip a little bit at the end, is that what happens if the patient moves during the scan? Well, we can model that as uncertainty in our measurement model. And we can still run the same algorithm, but now we can solve for the motion parameters at the same time. And so I'm running the same method, but now I'm getting an image that was originally corrupted by motion. And so this is what the image would look like if I didn't account for motion in the model, but I'm able to recover not only the image, but also the motion that happens during the scan. And so in this way, I can recover simple motion artifacts that would happen during a typical acquisition. All right, I'm gonna stop here, but I'll just mention a word of caution. I would recommend that you check out our paper on misusing and abusing data from the web. All right, so we call that big data small crimes. And I'll just skip ahead to the conclusion and just mention that I think that robustness to conditions at test time is really what's critical to getting these things to be used in the clinic. And I believe that using generative models is one way to achieve that goal. And with that, I would like to acknowledge all the members in my lab, our collaborators, our funding, and maybe you in the future. Thank you.
We have time for a few questions for John.
Okay, nice presentation. I was wondering if, you're dealing with Gaussian noise. What if the noise is not Gaussian? How do you deal with those problems?
Yeah, that's a good question. The question is kind of a technical detail. I actually didn't mention that we're dealing with Gaussian noise, but you're right, we are. If you're dealing with a different kind of noise model, then you just have to bake that into the posterior. That's what's nice, is that we're decoupling the measurement model from the image prior. So we would train the image prior in the same way, but we would change the P of X given Y would decouple into a likelihood term that would change. And so it can handle different types of noise distributions.
Any other questions for John? Okay. If not, let's thank John again.
All right, thank you very much.